Good day, Dr. T here. Welcome to my office. So today I'd like to talk a bit about gases. When we think about gases, typically the way we think about them is in a method known as the kinetic molecular theory. The idea is that gases are made up of small particles, whether they be molecules or occasionally individual atoms, and that these molecules and atoms are all moving. They're bouncing around like crazy. And if we think about how they're bouncing around, this can tell us a lot about gases and the properties that we'll expect from gases. So there's four major properties that gases have, or four major properties that we look at for gases. The first is temperature, which is a rough description of the kinetic energy that the particles have. Now, they don't all have the same kinetic energy. Some will be moving faster, some will be moving slower, and as such, they will have a variety of kinetic energies. Typically, you can plot that on a Gaussian distribution, a nice bell curve. But you can look at their average kinetic energies, and this is going to be related to their temperature. So if you understand their temperature, you basically get an idea of how fast they're moving, or relative to their weight. The next property is going to be volume. How much space are they taking up? Now, here's where things can differ a little bit. We have two concepts of gases, what we call ideal gases and real gases. Ideal gases make a few simplifications. These simplifications are generally valid most of the time, but not always, and they're not necessarily extremely valid. They're reasonably valid. So for most applications, ideal gases work. However, if you need very high precision or you're working under somewhat extreme circumstances, then you can't make those assumptions and you need to use real gases, which real gases are simply ideal gases where you didn't make those assumptions. When we're thinking of volume, we can think about the volume of the container and assume that the volume of the individual particles of gases are relatively small. So the atoms and molecules don't take up that much space. So the space in which they have to bounce around, which is the actual volume that we're talking about, is the same as the volume of the container. This is an ideal gas. However, if you cram a whole lot of gas into a container and pack it in real tight, then all of a sudden a significant volume of that container is actually full of, atom. So you can't make that assumption, and we'll need to do some corrections for that depending on the size of each of the individual atoms. The next property that we typically look at is going to be just how much gas is there. This is going to be measured in moles, so basically a count. But how many particles do you have? Now here's the interesting feature here. Gases typically all interact relatively similar, especially when we're dealing with ideal gases. The assumptions that we make assume that they're basically all the same. So a mole of this or a mole of that are all the same. So when we're talking about amounts of gases, we may be dealing with amounts of an individual gas or the amounts of a mixture of gases. Either way, the gas laws generally describe the same properties. If you're dealing with real gases, things can get a little bit more interesting, but you still get the general idea. The fourth property is pressure, and this one I saved for last because it's a little bit more complicated. Roughly speaking, this is the force exerted on the walls of the container by the gas particles slamming into them. They're bouncing around chaotically within your container, and as such, they're pushing on the sides. That force is known as pressure. There's a couple of different ways to measure this. You can measure the amount of force in standard force units, such as newtons, over an area, such as square meters, which gives you the Pascal. Alternatively, you could measure the pressure based on how high it can push a liquid up a straw that's been evacuated. So how high a vacuum can pull a specific liquid. Typically, said liquid is mercury because it's very dense and not particularly volatile. And so you can have things like millimeters of mercury, which describes how many millimeters that pressure of gas is able to push a column of mercury up. Roughly speaking, normal atmospheric pressure is going to be something around 760 millimeters of mercury, or 101,000 pascals, or 101 kilopascals. The third way is what I just did there, and that is do a relative measurement. The unit of atmosphere is quite often used. If it's 1 atmosphere, it's the same as the average pressure at sea level. If it's half an atmosphere, it's half of that. If it's 2 atmospheres, it's twice that, and so on and so forth. Now, when we're thinking about pressure, this can give us a couple of insights. For starters, of course, how strong a container do we need? If it's pushing on quite hard, you can have a lot of force for a gas, and that can be quite impressive. Keep in mind, mercury is particularly heavy. 760 millimeters is a smidgen over 3/4 of a meter. That's a pretty good stretch to push up a column of heavy metal that just happens to be liquid. And that's just at 1 atmosphere. Imagine if you're dealing with something even higher pressure. The other reasons we might want to think about pressure are a couple of fold. For starters, if you're able to know pressure, volume, the number of moles, and the temperature, well, actually I should say if you know any 3 of those 4, you can know all 4 of them using what's known as the ideal gas law. This is assuming that you are dealing with ideal gases and not real gases. There is a modified law known as the real gas law in which takes account of the 2 assumptions. The one I already mentioned about the atoms actually taking up space. The other one is the assumption that in ideal gases, the atoms and molecules don't stick to each other. They simply bounce off when they collide. This isn't strictly true, but typically the amount of sticking they do to each other is small enough that it's negligible. That said, if it's not negligible, you do have to account for that. A third point to consider with respect to pressure is that pressure can be a proxy for chemical reactivity. For chemicals to react, 2 atoms have to actually collide. Of course, whether or not they collide deals with how many of them you have, and the collisions of low velocity aren't going to be sufficient to arrange the electrons such that you actually get a reaction. So you need to collide and collide with enough force. Pressure is a function of both volume and number of moles, so concentration, as well as the temperature, so the amount of force you have. Thus, at high pressures, you're going to have lots of collisions. At low pressures, you're going to have fewer collisions. As such, at higher pressures for a particular gas, then you can expect faster chemical reactions. If the gases are blended together, and there's only one gas that you're particularly interested in, you can work with what's known as a partial pressure. Partial pressure is the pressure of just that particular gas, ignoring all of the others in the mixture. If you think about, say, combustion taking place, if you've got normal atmospheric pressure with normal oxygen concentrations, then you're looking at a partial pressure of about 0.2 atmospheres, and that's nice normal combustion. If you increase this even modestly, the rate of combustion will increase significantly. This is why emphysema patients who are on oxygen have notes on their door that says absolutely no smoking or open flames within the house, because if something were to try and catch on fire, it would do so much easier and at a much greater rate than normally would be expected. There are several horror stories of people's houses burning down in very short order because they were on oxygen and they were smoking. Don't smoke. Now, when dealing with looking at pressure and volume and quantity of gases, there's a couple of what we call named gas laws. These laws were developed some of the early days of chemistry. This was some of the foundations of chemistry, although a few of them were developed a little bit later. In general, the naming of the law is more historical. What you're looking at is relationships between properties. So the 4 major properties, temperature, pressure, volume, and number of moles, can be described either as a set for one particular quantity of gas by the ideal gas law, or can be described from a group of gases that is starting out at one condition and then changing by using the combined gas law. With respect to the combined gas law, if a certain property is held constant, potentially you don't know it, but you know it doesn't change. Let's say you know there's no leak, but you don't know the moles of gas in your container. You can simply remove that from the combined gas law, and it does not affect the mathematics involved. Remove a sufficient number of these, and you lead to the named gas laws, such as if you only have pressure and volume, so you have an initial pressure and volume, and you have a final pressure and volume, you get Boyle's law. Temperature and pressure, you've got Gay-Lussac's law, and so on and so forth. There are several of these. So to conclude, gases are an interesting topic. These were some of the first areas that chemists explored because their physical properties actually don't depend too much on the identity of the individual gas, as long as you're within a reasonable approximation of an ideal gas. And understanding their properties and the relationships between temperature, pressure, volume, and the amount of gas you have leads to quite a few everyday phenomena. So with that said, have a wonderful day.